Hello, I'm Paul Beckwith, and this video is a continuation of my discussion, which is basically on a mishmash of some of the most significant climate change events that have been occurring in the last little while. So I'm going through my Twitter feed where I've collected what I think are the most significant events. So this is where I ended up on the last video. So this is showing how global warming is changing the temperatures on the Earth. So you can see here, this is the temperature rise here. This is from 1850 to 2018. Okay, so this is envelope of curves. As this is sort of the distribution. This will be the mean temperature anomaly. And this will be the high tail where the temperatures are much warmer than the mean, and this is the low tail where the temperatures are lower than the mean. And what you see is this mean shifting up to warmer and warmer temperatures over the year, the average being measured here, and this is the envelope of curves throughout the year, and that kind of gives you an idea of the distribution of temperatures around that mean rise. So some areas are getting much warmer than the mean. For example, over land, the rate of warming over land is double that of the oceans. The rate of warming in the Arctic is 2 to 3 times faster than the global average. The rate of warming at elevated areas on mountaintops is about double the rate of warming, and so on. So let's play this video. Okay, so this is a year. So this red line here is the mean, and it's plotted on this curve here. So you can see there is variation from year to year. It doesn't increase just the same uniformly every single year, right? There's internal variability like El Nino, La Nino. There's different volcanoes going off that might cool a couple of years relative to others. But generally, the change in the chemistry of the atmosphere and the oceans, the increase of greenhouse gases is trapping more and more heat, and we're seeing this rise. And what you can also notice is that the rate of change of the rise is accelerating. Okay, it's not just a linear curve. We're getting warmer and warmer much more quickly. So I just want to play this a second time. Okay, also you can see that the distribution of the curve, which is how the temperatures vary across the planet relative to that mean, is also not constant. If the peak is higher and higher, it means that there's more and more temperatures closer to the mean. So we can talk about the width of the curve or the variability. And if the curve is flattening out, not as high, and wider, then basically that's the width is an indication of the variability. Also, the curve is skewed to the right often. So, if more of the curve, so the shape of the curve from the peak down to the left is often sharper. And see, if you look at the peak here, the drop is sharper here on the cold side, and it's got a very long tail on the warm side. So this is saying that there's a lot more, heat and extreme weather events, heat waves and stuff, than there are cold events, which is also, no surprise. Okay, so this is an excellent way of portraying. So climate change, not stopping, not even slowing down. We need climate action now. I mean, this is a great depiction of what's actually happening. Climate change doesn't get clearer than this. This is an interesting plot of the interesting image diagram. Is from the IPCC, Intergovernmental Panel on Climate Change, the Assessment Report 5. This is a carbon cycle showing the stocks and fluxes of carbon in the atmosphere, biosphere, and oceans, but numbers in red indicate the difference from pre-industrial. So what you can see is, look at these. So this didn't exist in pre-industrial. So this is fossil fuel, coal, oil, gas, cement production. The units are in petagrams of carbon per year. And so you can see, you know, a huge red line here that didn't exist before. Net land use change. As we clear the land, we're reducing the sink, so more of that carbon's in the atmosphere. This is respiration and fire. So there's fires are taking more of the organic material from the Earth's surface, and that carbon's going up into the atmosphere. There's more of this carbon is now being absorbed into the oceans. Okay, you know, 80 now. It used to be 60, so there's a gain of 20 petagrams of carbon per year going into the oceans, and there's more coming out of the oceans, but not a balance. So the net going into the oceans will be the difference of this, which is 2.3. Going into the oceans is the net. And that goes down into the deep oceans, so there's more going down into the intermediate and deep oceans by vertical transport in the oceans and so on. Okay, the reserves of fossil fuel, this is how much we've used up since the from pre-industrial and so on. So there's lots of good information here on how we've changed the carbon cycle. Now, this stuff was known years ago. So 37 years ago, this is a graph. It's freaky and horrifying how accurate Exxon's 37-year-old predictions for carbon dioxide levels today are. So let's have a look at this. So what you can see is, so this 37 years ago, Exxon had this growth of atmospheric CO2 and average global temperature increase as a function of time. This was the most probable, and this was the high end of their model. And here we are in 2019. And the average temperature increase, they said, would be about 0.85 to 0.9 degrees Celsius. And the CO2 level at the high end would be 420. And we're, 415. This is just under 420. Okay, so they knew exactly what was going on, and yet they funded denial groups, etc., for years and years and prevented action on climate change. Okay, so CO2 has recently, surpassed 415 parts per million. This is a compilation going back, this is CO2 parts per million going back 3.5 million years. The last time CO2 was this high was 2.5 million years ago. So this is thousands of years before present. So multiply this by 1,000, that's 2.5 billion years. CO2 levels were here, about 415, matching what they are now. So you have to go back 2.5 million years. At this time, sea levels were 10 to 20 meters higher. Global average temperature was plus 3 degrees Celsius warmer. So all things being equal, we've pushed the system so hard it hasn't responded to the full capacity. So if we froze the levels of CO2 in the atmosphere now at what they are, then we could expect over a long period of time for sea levels to rise 10 to 20 meters and for the temperatures to warm to plus 3 degrees Celsius. We've overshot clearly. We have no choice but to deploy carbon dioxide removal techniques to lower carbon dioxide down to a safe level. 350 now, the whole premise was it was 350 parts per million that was a safe level, down from 415 is what we are now. But it looks more like 300 parts per million is required. So we have to try to restore a healthy climate, Google Healthy Climate Alliance, and get CO2 levels back down to the 300 part per million level. Okay, some people say that rising CO2 levels are due to volcanoes. Okay, so this is clearly refuted here from chemistry. Look, this is depletion of oxygen from the atmosphere. Every time you burn a fossil fuel and generate carbon dioxide, you're removing 2 oxygens from the atmosphere. Okay, so the oxygen level, as CO2 is rising exponentially, the oxygen level is decreasing exponentially. This is measured at various places around the planet. And this is, if you smooth out the seasonal variation, take the average of each of these curves, then you have this. So the northern hemisphere leads the southern hemisphere in declining oxygen. The northern hemisphere is shown in the cool colors, these colors at the bottom. So it's dropping faster. The southern hemisphere oxygen is in the reds and the lighter colors. It's dropping about the same rate, but it's offset at a higher value. Okay, so just like most of the CO2 emissions are in the northern hemisphere, where land is and industry, and most people are living, producing more CO2 in the northern hemisphere, we'd expect the oxygen to be lower in the northern hemisphere. And that's exactly what it is from this curve. This is, of course, Greta Thunberg, okay, who's been the leader of the, she says here, now I'm speaking to the whole world. Yes, Greta, you are. If you're on the cover of Time magazine, you're speaking to the whole world. You know, great picture of her, the teenager on strike for the planet. It is a Friday when I'm doing these videos. I should be out on the streets with these students striking, but I thought this was a day to film videos. Okay, this is another graph showing we've got the carbon emissions from fossil fuels, carbon emissions from deforestation, okay, added on top, and then this is the oxygen, annual world oxygen depletion. So you can see it's tracking exactly. We're emitting, burning and emitting carbon. We're deforesting land. That decreases the sink, the amount of carbon captured by vegetation on the land. So that causes a rise here, and oxygen depletion is tracking this precisely. So it all makes sense. This is you know, this is some, I was talking here, this is a local part of Ottawa, very beautiful area, cherry tree in the background, and I'm talking about ways to make your house more resilient from flooding. You know, whether you're on a river, whether you're on, you know, just an area, you know, you don't have to be on a river, okay? If you can be anywhere, and these torrential rains, if water pools near your house in your region, you can get flooding. So what can you do to make yourself as resilient as possible? Gavin Smith, this is Goddard Institute of Space Science. They have their temperature map and his projection for what's happening in 2019. His projection is here. So this is the year to date mean anomalies. These are the predictions. So, you know, here we are. So we're continuing to warm. This is very interesting. Okay, so this is the mean Arctic temperatures throughout the year. Okay, so look at all of the. Okay, so 2018, there was a lot of. So most of the warming. This is January here to December. Okay, so most of the warming is happening in the winter months. And actually, if you look at the line, if you look at the lines here, it's colder. It's actually getting a bit colder in the summer months. And this is because so much ice is fractured and broken. The surface area of the ice is much, much larger. And it's absorbing a lot of course, it's taking in more and more of the energy from the sun to melt the ice. So the latent heat effect is happening. Now, as soon as the sea ice, so what's going to happen is, you can clearly see what's going to happen. When there's no more sea ice in the Arctic, see this spread here above the average? This is going to continue up here, and it's going to continue up here. So this fluctuation, this huge temperature rise in the winter, is no longer going to dominate. What we see, the temperature rise in the winter, is going to also occur in the summer, basically. So the scatter of red here will be up like this, way up here, you know, about the same level as it is in the winter. And that's clearly what's going to happen when there's no latent heat effect. So the Arctic temperature rise will skyrocket. And of course, Greenland is exposed. Melt rates from Greenland will greatly accelerate, and we'll be in a quite different world when that happens. And it's going to disrupt global food supplies, I'm convinced. So, yeah, this graph is crucial for understanding what's going to happen with the blue ocean event. Thanks.